Okay, so we're going to talk about physical optics now, and physical optics deals with the wave nature of light. So far, when we were doing geometric optics, we haven't been necessarily focusing on the fact that like light is physically like a wave with crests and troughs. We've just been thinking about the ray nature of light, and now we're going to kind of look at the idea that light has crests and troughs, and it can interfere with other light, and kind of what happens with that. So a few things we need to kind of prime ourselves and kind of remind ourselves about with light waves is the fact, just reminding ourselves that when a wave goes into a new medium, the frequency stays the same, but the velocity of the wave, the speed of the wave, and the wavelength of the wave, it does change. So when light goes into a new medium, the frequency stays the same. But the speed, the velocity, and the wavelength do change. So wobbly. That didn't help. And so there is a mathematical formula that shows exactly how that wavelength changes. I'm not going to go through the derivation of that. If you want to see the derivation, come find me. The derivation is also in your textbook. But essentially, the wavelength in a given medium, okay, so this is lambda sub n. The wavelength in the medium is equal to the wavelength in air divided by the index of refraction of the medium. So just kind of to note, this is the wavelength of the wave in air. And then this is the index of refraction of the medium. Okay, so this is how you could figure out what the wavelength in the particular medium is going to be. So the first thing we're going to look at with the wave nature of light is something called diffraction. So diffraction occurs when if a wave encounters a boundary or an opening rather, when a wave encounters an opening in a boundary that is comparable to the size of the wavelength of the wave. So that's a mouthful. Let me write that out. So when a wave encounters an opening in a boundary whose size is comparable to the wavelength of the wave, the wave diffracts out after passing through the opening. And essentially this idea of diffracting is the wave begins to spread out in a circular pattern. So what that kind of looks like is if I have, so this is like my barrier, my medium, or my kind of interface. And let's say I have a wave. Now, when we're thinking about waves and drawing light waves, we are taking into account the fact that there is a peak and a trough, but it's really, sometimes it's kind of hard to like visualize it like this. And so another way to kind of think about it is like thinking about looking at it from like a top view down. So like where we see a line, there's a crest, and when we don't see a line, that's a trough. So we can kind of like visualize like these waves are like coming in this direction. But rather than like drawing them like a transverse wave, we just draw like these lines are representing the peaks, okay? So instead of drawing the blue, we would draw, like, these are the peaks of the wave. And these are called, like, wavelets. Okay, so you can imagine this wave is like going, it's moving in this direction, it's about to encounter this interface, and then there's a hole in the interface. Now this idea where it says whose size is comparable to the wavelength of the wave, what I'm saying is the size of this hole, this opening, is comparable to the size of this wave, like this length between my waves. So this hole or this opening is comparable in size to the distance between my waves. You're going to have this diffraction occurring, or this spreading out in a circular path. So when the wave hits here, so imagine, you know, this wave front is about to hit this opening, clearly the waves that are hitting the boundary, they're just going to reflect back. They are not going to make it to the medium. And only like this portion of the wave actually passes through the boundary, the opening. And it's going to diffract out. So it's going to actually, like that part goes through, but when it gets to this boundary here, this opening, it's going to start to spread out and kind of travel out in a circular pattern. The wavelength is not going to change. Like, I'm still going to have the same spacing between my waves. My frequency is not changing. I'm not entering into a new medium. I've just kind of constricted how much can actually go into this new region, and because of that, the wave then kind of spreads out. So this is the idea of diffraction, where the portion of the wave that makes it past the boundary diffracts out, it spreads out. This is this happens with all waves, not just sound waves, not just light waves. It happens with sound waves in the idea, like, here I am, I'm talking in this room, but if the door opens, like, the sound wave is going to pass through that opening of the door, and it's going to spread out in every direction. So even though, like, I'm talking in this room and the door is over there, someone on the other, like, physical side of the wall is able to hear me. Like, if I'm standing here talking, my sound waves are definitely, like, they're going out in every direction. And if this is like the door, those sound waves are going out in every direction, and the sound waves that come out of here, they're going to diffract out. And someone who's behind me on their side of the wall can hear those waves because of the fact that they diffracted out of the doorway. Okay, so diffraction happens with all waves as long as the size of the opening that wave is passing through is comparable to the size of the wavelength of that wave. Okay, so now that we kind of have a base idea of a diffraction, we're going to talk about a pretty famous experiment with diffraction that you guys will actually conduct in class, and it's called Young's double slit experiment. So this guy, he kind of took this idea of like diffraction and understanding the concept of diffraction, how the wave is going to spread out, and he actually did it where there was two openings in the medium. So I'm going to kind of bore you to death a little bit in that I'm going to just kind of front load you with what the experiment is, and then I'm going to physically try to model it here on the board, and then the video will stop and I will kind of transition to kind of going through an animation to hopefully give you a visual, and then we'll come back and I'll kind of show the mathematics of it, okay? So this first little part is going to kind of be a lot of notes. You may have to pause the video because I'm not going to be writing it live. So Young's double slit experiment. Essentially, what happens is light from a monochromatic source strikes two slits on an initial surface. Okay, and we're going to call that slit 1 and slit 2. Monochromatic, that's the idea of it's of a single wavelength. We will, when you guys come back in class, we will talk about what happens when you use non-single wavelength, like not just like a red laser or a green laser or a blue laser. What happens if you do this with white light? And it's amazing. And we'll talk about that when we get back in class. But first, let's just make it a little easier and look at the original experiment which just dealt with one frequency of light. So this light from a monochromatic source strikes two slits on initial surface, S1 and S2. The light emerging from the slits diffracts, sending out overlapping waves that will interfere with each other. Okay? So again, pause the video, write this down. And then points where the waves are in phase will interfere constructively to form a bright spot, and points where the waves are completely out of phase will interfere destructively to form a dark spot. So we're kind of building on our idea of constructive and destructive interference. We looked about this a little bit. We had a taste of this with sound waves when we were talking about the idea of the person standing here and the sound wave from this speaker is coming this way, and the sound wave from the speaker is coming this way. And if they hit your ear and they are both in phase with each other, we're going to hear it's going to be constructive interference. But if when they hit your ear, one is at like a peak and the other is at a trough, we're going to have destructive interference. We see the same thing happening with light. So again, where the waves are in phase are going to have constructive interference. Where the waves are out of phase, there's going to be destructive interference. And these regions are known as maxima, or we might call them antinodes, another kind of terminology we're bringing in from waves. And minima, these are where there's the destructive interference, and we have these nodes, okay? So if you need to, pause the video, get these notes down. And something to note is that the further away the constructive interference is from the slits, the smaller the intensity is. And that is just because as that light wave like travels outwards, it's physically, the light is being spread out over a bigger area, so the intensity is going to drop. And we see that with all sorts of waves. We see that with sound waves. We see that with light waves. The further away you get from the source, the weaker the signal is, so the amplitude is going to decrease. And in terms of a light wave, the amplitude is associated with the brightness of the wave. Okay? Okay, so hopefully you kind of have this down, and now I want to kind of physically draw it out for you. And I'm going to draw it out two ways. The first way I'm going to draw it out is with how I kind of did before with this idea of like these wave fronts, and then I will model it with the actual like transverse wave of peaks and troughs, okay? So what we're going to have is, I'm sending like, so this is my first kind of boundary, and this is like slit 1, and this is my slit 2. And my light waves are going to come from here, and then they're going to go through these two slits. So I'm going to kind of model that. So here's like my peak, my peak, my peak, my peak. I'm just sending these continual like light waves through this region. It strikes this kind of interface here, and again, only the light that strikes the holes or the slits makes it through, okay? And what happens is when it strikes that slit, it is going to diffract out. So what that looks like here, and I'll try to do this with somewhat neatness. Whew. I should have made my two spots closer to each other. Got a lot of circles here. That wasn't as good. Okay, so this is the light from this slit. Now, it's the same frequency, but just for a visual purpose, I'm going to draw the light that's coming out of this slit, the diffraction that's coming out of this slit, just as a different color, so you can kind of see the overlapping. But I want you to know that just because the light goes through the slit, it doesn't magically change its frequency. But again, for visual purposes, I'm just going to do it in blue, so you can see, okay, the red represents the light that's diffracting from slit 2, and the blue is going to represent the light that's diffracting from slit 1. Okay? So again, same thing. We're going to have this diffraction. I'm going to try to keep them the same wavelength because, oh, got a little wonky there. Oh, could be better. Ooh, okay. So this is what I mean when I say in the notes, so where is it? Here. That the light emerging from the slits diffracts, sending out overlapping waves that will interfere with each other, okay? So slit 1 sends out these are represented as blue waves. Slit 2 sends out the ones that are represented in red waves. And where the waves are in phase with each other, there's going to be constructive interference. So remember, the lines that I am physically drawing are representing the peaks, and where there is no line, that's a trough, okay? So I kind of like the translation here is like, this is a peak, this is a trough, a peak, a trough, a peak, a trough, a peak, a trough. So where I have a line, that's a peak. Where there is no line, that's a trough. So I'll say it right here, at that point in space, the red wave, the wave from slit 2 is at a peak, but the wave from slit 1, the blue, is at a trough. So they're out of phase with each other. So at that point right there, you would have destructive interference. At this point right here, okay, my wave from slit 2, my red wave, is at a peak. My wave from slit 1, blue, it's at a peak. So right there, you would have constructive interference, okay? So you get this pattern of like, there's constructive, and maybe I could, I don't know, but I'm not skilled. There's constructive right here. There's destructive. There's constructive. There's destructive. There's constructive. There's destructive. There's constructive. There's destructive. And you get this pattern of constructive interference, destructive interference, constructive interference, destructive interference. It's like a standing wave when we saw with like the long slinky of science, okay? And so we get these bright spots of constructive interference, and those are called maxima, and we get these dark spots where there's destructive interference, those are called minima. And if you have like a screen here on the side where it actually like the light hits something, you'd have like a really, really, really bright spot, actually here, you'd have this really, really bright spot here, really bright, and then you'd have dark, and then on this side you'd have dark, and then you'd have bright, but not as bright. So I'm just going to draw it like smaller physically, my words, and you'd have bright. And the reason why it's not as bright is because it's further away. The intensity is going to drop. And then you have dark. And dark is still dark. Like absence of light is absence of light. You can't like have a change in intensity of absence of light. This is still dark. And then you have bright, but again, it's not as intense. And you have bright. Okay. Another way to kind of visualize this. So this is a good visual. If you want to draw this, you could pause the video and you could draw this. You don't have to draw this. Up to you. I'm going to do the same kind of idea, but with like my waves of science. Okay. So we've talked in the past that like when waves like are completely in phase with each other. So I have two waves, they're completely in phase with each other, they would constructively interfere. So you can see crest and crest, trough and trough, where they end, like I'm right here, they would add up to constructive interference. But if instead I had these two waves, these are completely out of phase with each other. So where one has a crest, the other has a trough. Right here, this one's like going on its way down, this one's going on its way up, I would have destructive interference. And so that's what we see happening when I have my light waves go through here. So instead of like showing like the model coming out here, I'm just gonna like show, you know, here's my light wave going through here, and here is my, I need another here, light going through here. So if I kind of think about this, like right here, oh, hold on, right here, like exactly opposite, like this length, I'll call it length 1, and if this is length 2, they're the same. Like the light that's traveling from this slit to this point is the same as the light traveling from this slit to this point. So if the lengths are the same, then the waves should be in phase with each other, completely in phase with each other, like this. And so right here, you'd have constructive interference. You'd get a bright spot, okay? So hopefully that makes sense. The lengths are the same. So because the lengths are the same, I'd have the exact same amount of waves traveling in that region, like wavelengths traveling in that region. So they would have a constructive interference point here. So I could write that as like a big, I don't remember what colors I used before. I think green was constructive. So I have a big constructive interference here. Now, take this away. If I think about like the light wave that traveled here, I'll call that L1, and the light wave that travels here, okay, now they're not the same length. They're not traveling the same length. One is traveling a little bit more than the other. And so there is this exact spot where one travels exactly a half wavelength more. So if it travels a half wavelength more. When this guy gets to here, like this, the other one travels exactly a half wavelength more. And so you can kind of see, I have this like half wavelength here. They're going to end up one being a peak, one being a trough, and they're going to cancel out. There's a spot right there where I am going to now have destructive interference. And the same can be true on the other side, where the length that this one travels, I'll call this L1, versus the length that this one travels, I'll call it L2. If L1 is exactly a half wavelength more than L2, then I'm going to have them offset. My two waves are going to be offset by a half wavelength. So same thing's going to happen. This guy's going to be like this, and this guy's going to be like this, because there's a half wavelength difference. And so right here, I'm going to have destructive interference. Now, let's keep going. What if, over here, again, they are different lengths, so one wave is going to travel a little bit further, but if the little bit further that length 2 is exactly a whole, like one wavelength, if it's exactly one wavelength longer, they should still be in phase. So even though this guy is like this, and I should have made it longer. I can do this. I can do this. I can just go like this. If it's a whole wavelength, so one whole wavelength longer, they'll end up at this point in phase with each other. And if it's in phase with each other, we're going to have constructive interference. It's not going to be as bright because this one had to travel further. So as it travels further, its intensity weakens. And then the same thing can be said for down here. So this guy travels a bit further than this guy, and if the extra length that this one travels is exactly a whole wavelength difference, so I can draw this again. If it's exactly a whole wavelength difference, I'm going to get constructive interference. Again, not as bright because this wave had to travel a little further. And we get this, it's a pattern. There's a point where a little bit further, this one is going to travel, and it's going to be a half wavelength off, and so I'll get destructive interference. A half wavelength off here, I'll get destructive. The next one would be when the path length difference is 2 wavelengths, and so I'd have, I need to go back to my green. So kind of pattern here is, for this one, the difference in length is equal to 0. 0 wavelengths. Like they travel the exact same distance. For this one, the difference in length is equal to 0.5 wavelengths, and same for this one. For here, the difference in wavelengths is equal to 1 wavelength, and again, 1 wavelength. Here it would be 1.5. Here it would be 2, and on and on and on. Okay. Another way to kind of represent like the brightness of the light, sometimes they show it with just like a graph, where you would see like really, like right here at this point, you'd have it be very intense. And so you could like graph the intensity of the wave, and it would be like, wow, that's really bright, and then it's really dark. And then it's bright but not as bright, and then it's dark. And then it's bright but then it's not as bright and dark. And then same here. I think I can, oh golly Mary. Where if this was like the intensity of light. You'd see it be bright, dark, bright, dark, bright, dark. Okay. Sometimes we call these fringes. This is the like 0th bright fringe. You should draw this. This is a good kind of visual. This is the 0 bright fringe. This is the first order bright fringe. This is the second bright. Now here's what's a little tricky. And on this side, this would be first as well. The counter always starts at 0. So technically this is like the 0th dark fringe because m is equal to 0. And this is the first dark. And when we look at the mathematics, hopefully that'll kind of make sense there. Okay. Okay, so I'm gonna kind of switch the format. The video is gonna switch to more of an animation, and I'm gonna kind of walk you through the same thing, but instead of like me trying to draw this out, the animation does a better job with the actual visual of this, okay?
Okay, so here is an animation that is showing Young's double slit, and this one actually it shows two screens, I guess. Here, this is the initial screen where it has like the light entering in, and there's just a single slit, and that single slit is just causing the diffraction to occur, and then you get the waves that hit this slit, and then the waves hit this slit, and you can see there's diffraction occurring in slit 1 up here. They're spreading out. They're happening here, slit 2. And what happens is when the waves from this first slit interfere with the waves from the second slit, they kind of visually show it as these dots. These dots are these points of constructive interference. And like right here, this point is destructive interference because there's a crest and a trough of one wave. Okay? And then here they actually show what the interference pattern would look like in terms of light. So here's where you have like this central maximum, this bright spot, and then a dark spot, and then bright, and then dark, and then bright. And you can see how the waves kind of these constructive interference points give you bright spots, and then these destructive points give you dark spots. Now, I want to show you just kind of some things that happen when you adjust different variables in the situation. So one of the variables you can adjust is the length, and the length, the L, is the length between the screen and where the slits are. And so if I move that over and see what happens to the interference pattern, look what's happening. Those bands of interference, they're becoming like just tighter. They're not as wide anymore. So as this distance shrinks, the width of the interference pattern shrinks. And so I'll show that if I make it further away, we'll see them get wider. Okay, so that's one of the things you can adjust. The other thing you can adjust is the distance between slit 1 and slit 2. So notice what's going to happen when I make the distance between them smaller. So those two slits are going to get closer together. Again, we see a widening here of our maximum. And so the central maximum gets wider, dark, wider, etc. And then if I make them further apart, oh, that was not further apart. If I make them further apart, they get thinner, and so they get closer to each other. And notice I had talked about this as well, how the intensity, the brightness of the interference pattern gets weaker the further away you get from this central maximum here. And that's just because as the light travels further and further away, the light, it's actually from here, it's going all the way up there, and it's decreasing in intensity. Okay. One last thing I want to show you is what happens if we change like the wavelength of the lights, the frequency of the lights. Right now we have red light and it's 600 nanometers. If I increase its frequency and I bring it, increasing its frequency, I have to decrease the wavelength. What's happening? You can see they're actually getting, you see how they changed? They got closer together. So I'm going to go the other way. I'll go back here. Here it was with red. Notice what's happening to the width of those maximums, those constructive interference points. It's getting smaller. Okay. So those are the things that affect where we have the constructive interference happening. We have the length between the slits and the screen. We have the distance between the two slits. We have the wavelength of the light. And we also, we're going to see, it also depends on like which maximum. Oh, let me change that back here. It also depends on what maximum we're talking about. So this is the 0 with the first order maximum. The 0 central maximum, first order, second order, third order, etc. Okay, so hopefully that gives you a better visual of what's happening with the double slit experiment.